Look up at the night sky. What do you see? You see countless points of light. Each one is a distant sun, a star. These stars are not just beautiful decorations in the cosmos. They are immense, powerful engines. They are gigantic furnaces, burning for billions of years. Their fuel is the simplest element in the universe, hydrogen. The process that powers them is called nuclear fusion. It is the same process that powers our own sun. It is the reason we have light and warmth. It is the reason life exists on Earth. This fundamental process is the creative force of the universe, forging new elements in the hearts of these stellar giants. Imagine the very core of our sun. The conditions there are almost unimaginable. The temperature is a staggering 15 million degrees Celsius. The pressure is immense, over 250 billion times the atmospheric pressure we experience on Earth. In this extreme environment, something truly remarkable happens. Hydrogen atoms, the lightest of all elements, are squeezed together with such incredible force that they overcome their natural repulsion. They fuse together to form a new, slightly heavier element, helium. This transformation isn't just a simple change. It is a profound act of creation that releases an enormous amount of energy. This released energy is the secret behind the sun's brilliance. A tiny fraction of the mass of the fusing hydrogen atoms is converted directly into energy. This is described by Einstein's famous equation, E equals mc squared. Because the speed of light is such a massive number, even a minuscule amount of mass can become a colossal amount of energy. This energy travels from the sun's core, taking hundreds of thousands of years to reach its surface. From there, it radiates out into space as light and heat, bathing our solar system in a constant stream of life-giving power, a gift from the stellar engine at our center. For millennia, we have looked at the stars and wondered about their nature. We now understand that they are all powered by this same fundamental mechanism. From the smallest red dwarfs to the most massive blue giants, fusion is the engine that drives them. It dictates their brightness, their color, and their lifespan. This process is not just happening far away in distant galaxies, it is the source of our own existence. Every second, our sun converts about 600 million tons of hydrogen into helium. In this video, we will embark on a journey to understand this cosmic fire and explore how we are learning to bring its incredible power down to Earth. For decades, the power of the stars has been a distant dream for humanity. We have looked to the sun and wondered, could we build our own star here on Earth? Could we harness the same clean, powerful process of nuclear fusion to power our cities and our homes? This is not science fiction. It is one of the greatest scientific and engineering challenges of our time. The goal is to create a controlled fusion reaction, a miniature sun in a laboratory that produces more energy than it consumes. Achieving this would change our world, offering a nearly limitless source of clean energy for generations. The promise of fusion energy is immense. It does not burn fossil fuels. It does not produce greenhouse gases. Its primary fuel, from water, is abundant worldwide. The process is inherently safer than nuclear fission. No risk of a runaway chain reaction or meltdown. Waste products are not long-lived radioactive materials. In essence, fusion would capture the sun's clean power and put it onto our electrical grid. This journey from understanding the cosmos to building a reactor is the story we will tell. We will explore the physics that govern the hearts of stars. We will witness stellar life cycles, birth in glowing nebulae, explosive deaths as supernovae, and the scattering of life's elements across the galaxy. Then we turn back to Earth. We will dive into machines that replicate stellar conditions, the massive international project ITER, and groundbreaking laser facilities that recently achieved ignition breakthroughs. The road to fusion is long and full of challenges. Recreating stellar core pressure and temperature is extraordinary engineering, but recent breakthroughs bring new optimism. Scientists have, for the first time, produced a fusion reaction that generated more energy than it took to start. This is a monumental milestone. It proves the Star on Earth dream is not fantasy. It's a tangible goal we are getting closer to. Join us as we explore the power of the stars and the quest to bring it home. To understand how stars fuse atoms, we must first appreciate the incredible forces at play. It all begins with gravity. A star is born from a vast cold cloud of gas and dust, mostly hydrogen. Gas, dust, mostly hydrogen. Gravity, the universal force of attraction, slowly pulls this material together. As the cloud collapses, it begins to spin and flatten. Spin, flatten. A dense clump forms at the center, the protostar. This central core is called a protostar. As more and more material falls inward, the pressure within this core begins to climb to extraordinary levels. Density within this core also climbs. It is this relentless gravitational squeeze that sets the stage for the miracle of fusion. This immense pressure has a direct and powerful effect on temperature. Imagine compressing a gas in a bicycle pump. It gets hot. Now scale that up to a cosmic level. In the core of a developing star, the particles of gas are being crushed together with unimaginable force. Particles, mostly protons, nuclei of hydrogen atoms. As they are forced closer together, they collide with increasing frequency and violence, jostling, crashing. This frantic motion is what we measure as temperature. The core heats up to millions of degrees Celsius. Now we have a problem, a fundamental barrier of nature. Every proton has a positive electrical charge. Like charges repel each other. This electrostatic repulsion is incredibly strong at short distances. It acts like an invisible shield, pushing protons apart. For fusion, protons must overcome this barrier. They must be forced so close a different, stronger force can take over. This is the ultimate challenge for a star to ignite its nuclear furnace. In stars like our Sun, the primary fusion process is a multi-step recipe known as the proton-proton chain. It transforms hydrogen into helium. It all starts with the most basic ingredient, protons. Two protons sometimes manage to fuse. This is the hardest step. Strong repulsion keeps them apart. When fusion succeeds, a transformation happens. One proton turns into a neutron. It releases a positron. It also releases a neutrino. The two-particle nucleus is deuterium, heavy hydrogen. The positron quickly meets an electron and they annihilate, producing high-energy gamma rays. The neutrino barely interacts and zips out of the sun. That first step is incredibly slow, billions of years for one proton. The second step is much faster. Deuterium floats among many hot protons. It collides with another proton within seconds. The fusion makes helium-3, two protons and one neutron. That reaction releases a gamma-ray photon, heating the core. Two helium-3 nuclei eventually meet. They fuse into helium-4, two protons, two neutrons. Two spare protons are kicked out to restart the chain. The helium-4 nucleus has slightly less mass than the four starting protons. That missing mass becomes energy, powering the sun and life on Earth. The life of a star begins not with a bang, but with a slow, silent gathering in the cold, dark corners of the universe. Across our galaxy and others, there exist vast, sprawling clouds of gas and dust. These are known as molecular clouds, or stellar nurseries. These clouds are truly immense, stretching for hundreds of light years and containing enough raw material to form thousands or even millions of stars like our Sun. For millions of years, these clouds drift peacefully through space. But tranquility doesn't last. Something must disturb the cloud. Shockwave from a nearby supernova explosion. That push creates slightly denser regions inside the cloud. Those clumps become centers of gravity, pulling in more gas and dust. As clumps grow, their gravity strengthens, a runaway collapse. The cloud fragments into hundreds or thousands of collapsing cores, potential stars. As each core collapses, gravitational energy converts into heat. The collapsing center, the protostar, grows hotter and denser. It glows from heat, emitting infrared light, not fusion, still shrouded in a thick cocoon of gas and dust. Eventually, the core is hot and dense enough for fusion. Temperature passes about 10 million degrees Celsius. Protons overcome repulsion and begin to fuse. A new star is born. Stellar winds blow away remaining gas and dust, revealing the newborn star. Once a star has ignited nuclear fusion in its core and achieved hydrostatic equilibrium, it enters the longest and most stable phase of its existence, the main sequence. Our own Sun is currently in the middle of its main sequence phase, and it has been for about 4.5 billion years. This stability is what allows planets like Earth to have a consistent climate over billions of years, providing the necessary conditions for life to evolve and flourish. A star's position on the main sequence is determined almost entirely by its mass. The term main sequence itself comes from a diagram that astronomers use called the Hertzsprung-Russell diagram. The duration of a star's main sequence lifetime depends entirely on how quickly it consumes its hydrogen fuel. A low-mass red dwarf will remain on the main sequence for trillions of years. Our Sun will remain on the main sequence for a total of about 10 billion years. A massive blue giant. Its main sequence lifetime is a fleeting cosmic moment, lasting only 10 million years or so. This phase ends when the star has exhausted the supply of hydrogen in its core. With the nuclear furnace at the center switched off, the outward thermal pressure that was holding gravity at bay suddenly disappears. Gravity immediately takes over and begins to crush the inert helium core. As the helium core contracts under gravity, its temperature and pressure skyrocket. The region just outside the core, a shell of hydrogen, is now heated by the collapsing core. This shell of hydrogen quickly reaches the critical temperature for fusion. This shell fusion is far more intense and rapid. This massive increase in outward pressure has a dramatic effect on the star's outer layers. The star begins to swell to an enormous size. The star's color changes from a bright yellow-white to a cooler orange or red, which is why it is called a red giant. A star like our Sun will expand so much that it will engulf the orbits of Mercury, Venus, and possibly Earth. When the center reaches about 100 million degrees Celsius, a new fusion process ignites, the triple alpha process. The result is a stable nucleus of carbon-12. In more massive stars, cores contract and can fuse carbon. This is followed by oxygen fusion, and then silicon fusion. The star develops an onion-like layered structure until it creates iron. Iron is the ultimate dead end for stellar fusion. Fusing iron nuclei does not release energy. With an iron core, the star's energy source is cut off. Gravity wins and the iron core collapses catastrophically. The collapsing material rebounds off the superdense core, creating a colossal shockwave. For a few weeks, a single exploding star can outshine its entire host galaxy. In the fiery chaos of the explosion, elements like gold, silver, and uranium are forged and then blasted out into space. The final chapter for a low-mass star like our Sun is a far more gentle affair. It sheds its outer layers, creating a beautiful, expanding cloud of gas. This glowing, expanding shell of gas is called a planetary nebula. The aftermath of a supernova explosion leaves behind a rapidly expanding remnant of gas and dust, and a bizarre, compact object at the heart, a neutron star. However, if the original star was exceptionally massive, the core collapses indefinitely, creating a region of space-time where gravity is so strong that nothing, not even light, can escape, a black hole. The carbon in our DNA, the calcium in our bones, the iron in our hemoglobin were all forged in the hearts of stars. We are, in a very real sense, made of stardust. The quest to harness nuclear fusion is one of the most ambitious scientific endeavors ever undertaken. The goal is to build a machine that can replicate the conditions inside a star. To achieve fusion on Earth efficiently, we need to reach over 100 million degrees. No physical container made of any known material can withstand such extreme heat. The leading design for this type of machine is called a tokamak, a Russian acronym that translates to toroidal chamber with magnetic coils. The charged particles in the plasma are forced to follow these magnetic field lines. This effectively traps the plasma, holding it in the center of the vacuum chamber. It creates a magnetic bottle. In modern machines like the International ITER project, they are made from superconducting materials, cooled to temperatures colder than deep space. Just meters away from the 100 million degree plasma, you have superconducting magnets cooled to minus 269 degrees Celsius. More recently, in 2021, it sustained a fusion reaction for 5 seconds, producing a record-breaking 59 megajoules of energy. While magnetic confinement seeks to hold plasma steady for long periods, there is another completely different approach, inertial confinement fusion, or ICF. The concept is to take a very small pellet of fuel and hit it from all sides with an incredible amount of energy. This outward explosion drives the rest of the fuel pellet inwards, compressing and heating it to stellar conditions. The world's largest facility, the National Ignition Facility, uses 192 beams, all converging on the center of a large target chamber. The target is precision engineering, a tiny pellet smaller than a peppercorn. The pellet sits inside a tiny hollow cylinder, a hohlraum, made of gold. Lasers don't hit the pellet directly. They hit the inner walls of the hohlraum. The X-rays flood the pellet and drive the implosion. The whole event takes a few billionths of a second. On December 5, 2022, a historic experiment took place at the National Ignition Facility in California. The facility's 192 giant lasers fired in unison, delivering 2.05 megajoules of energy to the hohlraum target. A few nanoseconds later, the diagnostics registered a massive burst of energy. The fusion reaction had produced 3.15 megajoules of energy, For the first time in history, a controlled fusion experiment had achieved scientific energy gain. It had produced more energy from fusion than the laser energy used to trigger it. This was a monumental achievement. It was a Wright brothers moment for fusion energy. The news of this breakthrough sent a wave of excitement through the scientific community and around the world. While this was a groundbreaking scientific success, it is not yet a power plant. The NIF lasers are incredibly inefficient, requiring hundreds of megajoules of electricity to produce just 2 megajoules of laser light. The world's biggest bet on fusion energy lies with the magnetic confinement approach, embodied in a single colossal project, ITER. It is a joint effort between 35 nations, representing more than half the world's population, have come together to build the world's largest and most powerful tokamak. Its primary scientific objective is to produce 500 megawatts of fusion power from an input of just 50 megawatts of heating power, a 10-fold energy gain. It will be the first fusion device to produce a burning plasma, where most of the plasma's heat comes from the fusion reactions themselves, rather than from external heating. The primary fuel cycle combines 2 heavy isotopes of hydrogen, deuterium and tritium. Deuterium can be easily and cheaply extracted from water. The oceans contain a virtually inexhaustible supply. The clever solution is to breed the tritium inside the fusion reactor itself. When the neutron strikes a lithium atom, it triggers a nuclear reaction that creates a new tritium atom. This tritium breeding cycle means that a fusion reactor can create its own fuel. The path to a commercial fusion power plant is still lined with significant challenges: developing materials that can withstand the extreme environment, achieving continuous, steady-state operation, and the economic challenge is real. We are standing at the threshold of a new age, an age powered by the same clean, abundant energy that fuels the cosmos. Imagine a world powered by fusion. We began our journey by looking up at the night sky. We have seen how this cosmic engine dictates the lives of stars. We brought our focus back to Earth. This cosmic-to-grid journey is about understanding nature and replicating it. The story of fusion is a profoundly human one. It is a testament to what we can achieve when we collaborate across borders and generations. The power of the stars is within our grasp. It is up to us to seize it. If you liked this video, please like, share, and subscribe.